Alright, so we're going to do the same question, but in a binomial kind of way. So we're still hunting for people who are in grade 9 and for people who are not. And I'm going to have to erase the board for some space, so let's do that. Alright, the difference between the geometric distribution and the binomial distribution is geometric, you keep hunting until you find one. A binomial is, I'm going to set how many people I'm going to ask, and then I'm going to count how many of them actually meet this criteria. So if I'm hunting for people who are not in grade 9, and I'm going to ask 5 people, then the outcomes are as follows. Maybe none of them are not in grade 9. Maybe one of them is not in grade 9. Maybe 2 of them are not in grade 9. Maybe 3 of them are not in grade 9. Maybe 4 are not in grade 9. And maybe 5, maybe all 5 of them are not in grade 9. So those are my options. It's quite a squeal this marker makes on the plastic. Now, to calculate the probabilities, if none of my people are not in grade 9, that means that all of them are in grade 9. Right? These things are mutually exclusive. So I must have five grade 9s and no, let's call them senior students just to save the confusion. If I find only one senior student, that means in my group of 5 people, 4 of them must have been in grade 9 and only 1 was a senior. If I find 2 people that are not in grade 9, then 3 of the 5 people I asked must be in grade 9 and 2 are not. If I find 3 people not in grade 9, that means the balance of 2 people had to be grade 9s. Four means there's only 1 grade 9 and 4 people who are not. And if I find 5 people not in grade 9, then none of them are in grade 9 and they're all in this pile here. Lovely. Okay. So, if I were to go through and actually do these multiplications, 0.25 to the exponent 5, let's see, 0.25 to the exponent 5 times 0.75 to the exponent 0 is 0.00097. So I'm going to round that to 0.00. I'll just keep 5 digits for this one. 098. If I were to go and do this row, 0.25 to the exponent 4, 0.25 to the exponent 4, multiplied by 0.75 is 0.00293. The next row, 0.25 cubed times 0.75 squared is 0.00879. The next row, 0.25 squared times 0.75 to the exponent 3 is 0.02637. And 0.25 times 0.75 to the exponent 4 is 0.07910. And my last row, 0.25 to the exponent 0 multiplied by 0.75 to the exponent 5 gives me 0.23730. Now if you were to look at these numbers and think about what's happened, I grabbed 5 people and I'm trying to figure out how many of them are in grade 9 and how many of them are not. Well, if you think about the possibilities, if you grab 5 people, either 5 of them are in grade 9, 5 of them are in grade 9, 4 of them are in grade 9, 3 of them are in grade 9, 2 of them are in grade 9, 1 of them is grade 9, or none of them are in grade 9. There aren't any other options. So I've covered everything. This chart does not go on forever, right? The next row would be 6. What's the probability of 6 of your 5 people being not in grade 9? Well, you can't have 6 out of 5. So this chart is done, which means these probabilities should add to 1, 100% chance. And they don't. That's 23. That's about 8. So we'll call that 24. That's about 8. So we're at 32. Call that 3. We're at 35. That's less than 1. We're at 36. And oops. We're a little shy. So there's a number here missing. You notice I've left a gap. Tactically, as always, left a gap there for something that we need to fill in still. So this part's a little hard to wrap your brain around. So the thing is, if I had 4 grade 9s and 1 person who's not a grade 9, so let's see. I might have found my not a grade 9 first, and then found 4 grade 9s. Because this is not a geometric distribution. I didn't stop when I found them. I just found 5 random people and asked. And maybe that's the non-grade 9, or maybe that's the non-grade 9. Or maybe this is the non-grade 9. Or maybe this is the non-grade 9. Or maybe it's not until the last one. So that non-grade 9, right, that one person who is not a grade 9 could be here, or here, or here, or here, or here. That means that there are 5 possible positions that that person could have been in. This one here, where they're all grade 9s, well, there's only one way to write that. He's a 9, he's a 9, he's a 9, he's a 9, he's a 9. There's only one way to write that out. So there's only one way for this one to occur. For this one, I've only got 3 9s and 2 non-9s. So they could have been, oh goodness. They could have been like this. They could have been like this. I'm just going to erase all of these. They could have been like this. Oh, hang on a second. Sorry for the hard cut. What are we doing? Right. That non-grade 9, they could have been stacked beside each other. Or it could have been like this. Or it could have been like this. Or like this. Well, that's all the options where there's a non-9 in front. So maybe a non, and then maybe like this. And then like this. And then like this. That's all of them where they're in the second position. So how about 9, a 9, a non, a non, a 9, a 9, a 9, a non, a 9, a non. If you're listening to me prattle on in the library, talking to myself about this, talking about nines and nons and nons and nines, it sounds really ridiculous. So rest assured, I haven't lost my mind. I'm just counting in an organized fashion. Last one, 9, 9, 9, non, non. Whew, there we go. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 different ways I could sort these non-grade 9s and grade 9s. So I'm going to need a 10 in front of this one. Now, I don't want to do this anymore. But if you can imagine in this row, every place, instead of 2 non-9s and 3 9s, I would have 3 non-9s and 2 9s. So everything that's a blue N would become a pink 9, and everything that's a pink 9 would become a blue N. In all of these different combinations, which would still lead to 10 different sortings. This one here, 1 grade 9 and 4 nons. Well, that grade 9 could have been in first position, second position, third position, fourth position, or fifth position. That's it. Total of 5. And there's only one way to draw 5 blue ends. Like that. And you notice the pattern went up and down symmetrically. I'm going to erase this mess here. We're going to fix these numbers because they're not quite right. This value here was okay because it's that multiplied by 1. That's not going to cause a change. But this one should have been multiplied by 5. So let's try that. 0.00293 multiplied by 5 gives me 0.01465. This row here should have been multiplied by 10 because there were 10 different sortings of these people. So 0.00879 times 10 gives me 0.0879. This one here, 0.02637 multiplied by 10 would be 0.2637. This row should have been multiplied by 5 for the 5 sortings. So 0.0791 multiplied by 5 gives me 0.3955. Now that I've corrected this, just to prove that this is the right thing to do, if I add this plus this plus this plus this plus this plus this, I should get 100%. So I'm going to give that a try. 0.2373 plus 0.3955 is that's 63%, plus 0.2637 is 89%, plus 0.0879 is 98.4%, plus 0.01465 is 99.905%, plus 0.00098 gives me 1. Almost right on the nose. There's a bit of a rounding error, but it's pretty close. So I need these numbers in front in order to adjust these probabilities up for all of the sortings of how those people appear. So here's my distribution table. I am going to circle back to these numbers and what they mean and where they come from after I do a little bit of work on this distribution. So patience. So we're going to have to ask those same questions that you were asked in the last distribution. What's the expectation value? And then what's the probability of finding this many or more than this or less than this? So if we try to do expectation values were the probability of something happening multiplied by the number of things you get for it. So if I'm hunting for non-grade 9 students, there's a 0.00098 probability multiplied by 0 gives me 0. A 0.01465 multiplied by 1 gives me 0.01465. 2 multiplied by this would be 2 times 0.0879 gives me 0.1758. 3 times 0.2637 gives me 0.7911. 4 times 0.3955 gives me 3.6045. And 5 no, I think I hit subtract, not multiply on that. Let's try that again. 4 times 0.3955, that's better. It's 1.582. And then 5 times 0.2373 gives me 1.1715. All right. Now to get an expectation value, I'm supposed to take all of these rows and add them up. And I don't have the problem last time where the table was infinite. I only have to add these 6 numbers. 5 actually, because adding 0 doesn't change anything. So 1.715 plus 1.582 plus 0.7911 plus 0.1758 plus 0.01465 gives me 3.735. Non-grade 9s. All right. Okay. Now, if you were to think about that, though, if 3/4 of people are not grade 9s, and I ask 5 people, then 3/4 of those 5 people should not be in grade 9. Well, 3/4 of 5 is 15/4, and 15 divided by 4 is 3.75. So I have a little bit of a rounding error here, but instead of doing all of that work to get the expectation value, I could have just used Manergan and realized that 3/4 of 5 people is 3.75. So if you ask 5 people and 3/4 of them should not be in grade 9, I would expect 3.75 of them to not be in grade 9. Now again, these decimals for people, I know that doesn't make sense. We're not supposed to be using these distributions on groups of 5. We're supposed to be using them on groups of 5,000. So put 3 zeros on the end of that, and suddenly this becomes 3,750, and which makes more sense. I just didn't want to make a chart with 5,000 rows in it, and neither do you, so you're welcome. So that's it. I'm going to shorten this up, though. You notice that this is the probability of finding the thing I wanted, and this is the number of people I asked. So I could summarize this for you, just like the geometric. I'm going to erase this, and I'm going to do that, and then we'll chat about it. So the binomial distribution is used to model a situation where you decide in advance how many people or how many objects you're going to sample. In this case, it was 5. And once you've decided how many you're going to check, all you're doing is counting how many of those meet the criteria you're after. So in the other example, the geometric series, the cookie jar problem was, I'm going to take off the lid and I'm going to keep throwing cookies in the garbage until I get the chocolate chip cookie I want. In a binomial way, I would dump 8 cookies on the counter and then see how many of them were chocolate chip. So if you're doing it that way and you're deciding you're going to ask this many people and it's either all of them, none of them, or some number in between, you're doing a binomial distribution and you model it this way. If that model applies, then the way you calculate your expectation value is to just take the number of things that you're going to check and multiply it by the probability of them meeting the criteria you're after. So now that I have the model built, what is the probability that out of 5 random people, 3 are grade 9s? Oh, 3 are not grade 9s. Okay, well that was this row on the chart. That's 3 people not in grade 9, so the probability of that should be 0.2637. That's pretty straightforward. Just like the geometric ones, we're just finding rows in the chart and then picking out the rows that we like. So question B, what is the probability that out of 5 random people, at least 4 are not in grade 9? Well, at least 4 means 4 or 5. That will do. So the probability for 4 of them is 0.395. And I'd have to add to that the probability of there being 5. This is 0.23730. For a total of 0.3955 plus 0.2373 is 0.6328. So there's a 63.28% chance that at least 4 of them are not in grade 9. So those questions are very similar to what you asked in geometric. The trick then is being able to identify whether a question is prompting you to use geometric or is prompting you to use binomial. So the words you're hunting for are out of. So this question, which was binomial, said, what's the probability that at least 4 out of 5 are not in grade 9? By saying out of 5, you are implying that I have pre-decided how many people I'm going to ask. And as soon as you've done that, as soon as you set a small chunk for your sample, then that's a binomial question. If the question had said, keep going until you find one, that's a geometric question. So try and keep that in your head when you're doing the problems, the practice problems, is trying to hunt and figure out which one's which. I would like to cycle back and talk about what these numbers are and where they came from, so I'm going to clear up some space so we can do that. So you may have come across a thing called Pascal's triangle, just as like a little math fact, somewhere in your elementary school time. And Pascal's triangle is just a neat little pattern. You start with 1, and then you start with 1 like this, so it's like the corners of a triangle. Now I'm going to add a row to this triangle. So I'm going to add a row on the outside, and a row on the outside. And you notice that this location here is located under this one and this one? Well, 1 and 1 is 2. If I were to add another row to this, 1, 1 on the outsides, this location is between a 1 and a 2. 1 plus 2 is 3. 2 plus 1 is 3. If I keep adding rows, a 1 on this side, a 1 on that side, 1 and 3 is 4, 3 and 3 is 6, 3 and 1 is 4. Add another row, 1 on the outside, 1 on the outside, 1 and 4 is 5, 4 and 6 is 10, 6 and 4 is 10, 4 and 1 is 5. Now, if you go back into where we were doing the binomial distribution question a minute ago, the coefficients that were down this side were 1, 5, 10, 10, 5, 1. And I generated those by finding all the different positions I could sort those grade 9s and non-grade 9s into. I didn't have to do that. I could have just grabbed a row of Pascal's triangle, which is super handy. So you should make an effort to find one of these, or to have one printed and sitting in your binder when you start to do these binomial questions, and certainly when we get to the next unit when we do counting theory, because these numbers and the sequence of numbers keeps coming up again and again and again. I'm going to add a few more rows just so we have some fun things to work with. 1 and 5 is 6, 5 and 10 is 15, 10 and 10 is 20, 10 and 5 is 15, 5 and 1 is 6, and then there's a 1 on the outside. Okay. So when you're doing a binomial question, I'm just going to write one down. I'll do it in fast forward mode so we don't have to get stuck on it. All right. So in the last geometric question, to try and give another example, I talked about left-handedness. So about 15% of people are left-handed. So if I were to ask 6 people, what is the probability that 2 of them are left-handed? Now that's binomial, because I'm going to ask 6 people. I'm not going to keep asking until I find one. I'm going to ask 6. So if I were to make this chart for the distribution, I would need to have, well, none of them are left-handed. 1 is left-handed, 2 is left-handed, 3, 4, 5, or all 6 are left-handed. That's 7 rows. Did you notice that this row here with the 6 in it has 1, 2, 3, 4, 5, 6, 7 rows. It's perfect. So if I were to build that chart, I'm going to erase this up here and use the space. Just quickly building the chart for this distribution, no left-handers, 1 left-hander, 2, 3, 4, 5, or all 6 are left-handed. I'm going to need to map these coefficients into the beginning of each of these categories. So 1, 6, 15, 20, 15, 6, 1. If there are no people who are left-handed, that means this 1 here is multiplied by 15%, showing up 0 times, and 15% are left-handed, then 85% are not. So there are none of these folks and 6 of these. In this row, there's 1 of this type of person, so there must only be 5 of this type. This row, there are 2 of this type of person, so there must only be 4 of those type. This is much faster than what we did before. It's the same thing as we did before, but I know the pattern in advance now. So I just have to jot these numbers in and then quickly calculate the values of each row. 0.15 squared, 0.85. Oop, nope, that's 5. 1. And this would be the probability that they're all left-handed. All right. Now the question asks, what is the probability that 2 of them are left-handed? Exactly 2. So that would be this row. So if I were to pluck that out of there, 0.15 squared times 0.85 to the exponent 4 times 15, oh, don't be doing that, times 15 is 0.1762 if I round. So there's a 17.62% chance that exactly 2 of them are left-handed. How many would you expect? Well, it's binomial, so the expectation of left-handers would be the number of people I ask multiplied by the probability of finding one. In this particular question, I asked 6 people, and there's a 15% chance of finding one. So 6 times 0.15, it's not that, 6 times 0.15 is 0.9. So I would expect to find 0.9 of a person who's left-handed. And again, we're not supposed to be using this on groups of 6. We're supposed to be using it on groups of 6,000. So out of 6,000, you would expect to find 900 left-handers. But this is just the mechanics of how it works.